Welcome to Physics Tips for Cambridge Students YouTube channel. Today we are going to be looking at uniform circular motion. This is the second video on this, and today we're going to be focusing on centripetal acceleration, centripetal force as well. So we are going to be looking at the forces that are going to be giving rise to this centripetal force. Because centripetal force is a resultant force towards the center of the circle when an object is undergoing circular motion. Without much further ado, let's get started. Now, when an object is moving in a circular motion, like I said, that the velocity is at a tangent to the circle. So what keeps this motion is the centripetal force, which is a center-seeking force. And the acceleration is also directed towards this resultant force, which is the centripetal force. So the resultant force, or this unbalanced force, is the centripetal force that we're talking about. It is needed in order for an object to keep moving in a circle. Otherwise, it would continue moving in a straight line according to Newton's first law. If you remember Newton's first law, saying that the body will always remain in the state of rest or in motion with constant speed unless an external force acts on it. So this object is moving in a straight line. So you've seen that if this centripetal force is removed, then this object will move at a tangent to this circle that it was describing. The resultant force is the centripetal force, which is center-seeking because it pulls the object towards the center. The centripetal force acts at right angles to the direction of motion. So there is no work done on the object because there is no movement in the direction of the force. Now, since kinetic energy and speed are scalar quantities, they remain unchanged. So what is changing is the velocity. I talked about this in my part 1 video. If you can watch that before watching this one, you understand the concept of linear velocity and the concept of angular velocity. Acceleration is the rate of change of velocity, so the object is accelerating. Applying Newton's second law, the rate of change of momentum is directly proportional to the resultant force and takes place in the direction of the force. That boils down to F is equal to ma, which is that. So the acceleration is directed in the same direction as the resultant force, or this centripetal force. So the acceleration is also called a centripetal acceleration. Now it can be proved that A is equal to V squared over R, and thus giving you A is equal to R omega squared. And the centripetal force from the second law, we substitute for A there, it becomes F is equal to mv squared over R using this, or m omega squared R using this one. Now the centripetal force may be due to a single force or a combination of several forces. For example, for an object whirling around the end of a string, the tension in the string is the centripetal force. For a satellite moving around the Earth, the force of gravity between the satellite and the Earth is the centripetal force. Now, in the video that I just showed you, that illustration, the force of attraction between the Earth and the Sun, here we're going to take this blue thing as the Earth, and then the Sun will be the red one. So the as it orbits around the Sun, we having the force of gravity between the two giving rise to this centripetal force. Now, for a capsule on the London Eye, the centripetal force is the resultant of the support on the capsule and the force of gravity on it. Now, proving that A is equal to V squared over R, we can draw our diagram. So say this object moves from A to B in a very short space of time. So the angle, the small angle that's going to be swept is d theta, right? And then the time taken is dt, which is a very small time. that is from A to B. The diagram has exaggerated so that we can be able to write down, but the angle that's going to be swept is very small. So it turns through the angle d theta when it moves from A to B at constant speed. The distance AB along the circle is the length of the arc, which is going to be equal v dt, because we know that the displacement or the distance traveled is equal to speed times time. Since this is constant speed times the time taken, so the small distance ds will be equal to v times the small distance time dt. The velocity direction of the object turns through the same angle d theta. Now the change in the velocity is dv. This dv is supposed to be towards the center, because from there we are going to derive the acceleration. We say that acceleration is always directed towards the center of the circle. So we derive the acceleration from this dv. So that's why we say it's supposed to be towards the center. Now if you look at these vectors, this vector is going up according to there. It mustn't change the orientation. But this vector has been reversed because we are subtracting in order for us to get delta v. So this has been reversed for the subtraction of vectors. So the velocity at B minus the velocity of A. So we have reversed this vector. So as shown on the triangle vectors, the change in the velocity dv is towards O and the acceleration is towards the center of the circle. The triangle ABO and the velocity vector triangles are similar since they have the same shape. So where we had ds is equal to v dt, we have dv is equal to velocity at B minus velocity at A. Now d theta is equal to ds over r. Remember, we from the length of the arc, that is the displacement. And then d theta is also equal to dv over v. Okay, that because the change is also directed towards the center, and we can take it as the radius over on the calculation. We take it as the radius, and then we have having dv. No, we cannot take it as the radius, but v we can take it as the radius of that. I think I need to show this. Let's see. Right. So our arc is going to be like this with our d theta. Then we have got s and r. So this should be the same as where we have our d theta again being equal to v, which is a constant variable, and then the change, which is dv. Okay. So this is ds. Okay, so these are similar triangles that we can take also, which you can say that dv over v should equal ds over v over r. So this is supposed to be r. Okay, so that's how it is. Now since we can equate these to d theta, so which means these should be the same. ds over r should be equal to dv over v. So that, which is that. But we know that ds is equal to v dt from this one. ds is equal to v dt from that. So we can substitute. And then we have the dv dt over r, which was our s, is equal to dv over v. Now dv by dt, right, is equal to this v goes and multiplies that, becomes v squared over r. Now dv by dt is acceleration. That's calculus. So acceleration is equal to v squared over r. Now since v is equal to omega r, we can also deduce v is equal to r omega squared. Okay, so we know that v is equal to omega r, right? And then a is equal to v squared over r, so which is equal to v squared is omega r all squared over r, which is equal to omega squared r squared over r, giving rise to that. Okay, so that's where it's coming from. Right, so I think that is that. for this video. In the last video, the part 3 video, I'll be looking at examples, that is the examples in in circular motion, working out examples. Please do not forget to subscribe to the channel and like the video and share to as many students as you can. Signing out.